Hi, everybody. Thanks for joining our webinar today. My name is Brent Cunningham from HORIBA. I'm going to be your facilitator today, and we'll be monitoring any questions or comments you have in the background. We'll also have some time for a Q&A session at the end. It is my great pleasure to introduce you to our speaker, Dr. Willie Hendrickson. Willie is the founder and CEO of Avika Group. Avika was founded in 1994 as a spinoff from 3M with 3 people in one site. So it's definitely grown since then. Prior to starting Avika, Willie worked at 3M as a technical manager for particle processing in 3M's corporate research facility. He has also authored or co-authored over 20 technical papers or book chapters, and is an inventor of 50 issued or applied for US patents. Received his PhD from the University of Florida. I'm very happy to have Willie. And if you are ready, Willie, I'll pass the ball over to you, and you can start sharing your screen.
Thank you, Brent. Welcome, everybody, for joining us today. I'm excited about giving a talk on jet milling and air classification. I call it a helpful guide to finer particles, or maybe a helpful guide to interesting particles, because I have a bit of some interesting structures to show you today. So let's get started with this. There, from an outline standpoint, I'm going to give you one slide overview of the company, just so you understand how we got to where we are and what we're doing. I'm going to talk about size reduction overview. I'm going to talk about classification overview. We're going to talk about some jet milling and air classification. I've got lots of examples to show you, and hopefully you'll find some of these interesting. If you've listened to my talks in the past, this is a talk that I gave 2 years ago. I've changed substantial portions of it, but there are some repeats in here. They were just too good of an examples not to include in this talk. So I hope you enjoy what you're going to see, and let's get started. From a standpoint of Vika, the Vika Group, we are a contract manufacturing company focused on particle technology. As Brett said, we are a spinoff from 3M. We started the company in 1994. We have over 300 customers a year, and we do 50 to 60 scale-up and development projects every year. The industries that we work in are shown at the bottom, anywhere from chemical to aerospace to food processing. We do a lot of work in the battery industry. And the process technologies that we do, even though today we're just talking about size reduction, jet milling and specifically, but we also do lots of other processes, spray drying, agglomeration, microencapsulation, membrane separation. But today we're gonna focus on size reduction and specifically on jet milling. So let's just look at size reduction overview. There's many different processes that you can use for size reduction, ranging from crushing, which is taking big boulders and crushing them down to smaller particles, to ball milling, hammer milling, jet milling, and bead milling. And each one of these processes actually have an application area that makes the most sense. You can see under each one of the processes that I list, a size distribution of the particles that you can get out of that process. So with the jet milling that we're going to be focusing on today, you're really looking at particles from the 1 to maybe 70 microns, maybe 100 microns. This is a technique to get you a small particle, not the bigger particles with hammer milling or crushing. There is a process to get smaller particles. Bead milling is a way to get particles below 1 micron. Typically, jet milling doesn't get you below 1 micron. The question always is that we get when people show up and ask us about these processes, size reduction, is which one should you use? And one is just the ultimate size that you're looking for, but sometimes it's the input size. Very hard to put a boulder into a jet mill, but it's very easy to put a boulder into a crusher, and then a ball miller, and then maybe a jet mill. The raw material that you use, there are some materials that really fit well with some of these techniques, and they don't fit very well with other techniques. If you're concerned about size distribution, one of these techniques might be better. If you're really concerned about energy efficiency, there's going to be some of these that are going to actually be absolutely the best. And in fact, we should just think about this a little bit. Energy is one of the interesting parts that we're considering on this. If you're a large-scale grinder at like a mining company or a cement company, energy is one of the most important issues. If you're a company grinding an API, a pharmaceutical ingredient, energy isn't the issue, but contamination and other things are. So lots of things to consider here. Let's just keep on with this energy a little bit. The amount of energy that it's going to take to break something is going to depend on the properties of the material. How hard it is, how plastic or ductile it is. You can imagine if you're trying to grind rubber, it might be a little hard to grind than something that shatters, that has crystallinity. And it also depends on the inherent defects that are in a material. So when we're looking at the mechanism of grinding, we're always looking for those defects in the material that when we hit it, it will actually cause that defect to increase its length and actually shatter the particle. These inherent defects, are ones that we start with, but in a grinding process, you're moving things around and you're hitting the particle multiple times. You're producing defects in there, and the amount of defects that you have are going to depend on this impact energy. One of the very interesting things about grinding, and as human beings, we've been doing grinding for tens of thousands of years, from breaking stones to doing APIs, but what we've found is that the actual energy utilization in most grinding operations is only 2 to 3%. So think about this. I mean, you're going through a whole grinding process, and most of the energy is going to just move the particles around, some losses in friction, some losses in plasticity, but only 2 to 3%. This has been studied for many years on all different types of grinding processes, as shown on this next slide, where von Rittinger, Kick, and Bond actually looked at the amount of specific energy that was used for different materials, and they came up with this graph that's remarkable in its consistency. So you can actually see that different materials like cement clinker or coal or plastics all kind of fit differently in this, and they've got this to the point where it's pretty well understood. You can see that there's less energy used for larger particles, which is not surprising, and an incredible amount of energy is shown here on the upper left hand that's needed to get the ultrafine particles. So one of the challenges that we have is how much energy, or another way of looking at this is how much time in the mill are we going to have to use to get the particle size that we want? Well, one of the things, this 2 to 3% energy utilization is really frustrating. I mean, considering that global warming and all this, some of these operations like making grinding cement clinker is one of the biggest energy uses in the world, and people have looked extensively on how to improve that energy utilization. And in the 50s, there was some work, some discoveries made in the use of what are called grinding aids. Now, in the cement industry that they're grinding up a tremendous amount of material, they found that if they added small amounts of liquid, and when I mean small amounts, I mean less than 0.1% of a liquid to a material, you could actually enhance the grinding efficiency, and it would grind 2 to 3 times faster. So in essence, instead of using 2% or 3% energy, you might be using 6% or 9% of the actual energy, which is an incredible example of energy improvement. Obviously, there's a lot more that can be gotten. On the right side here, there's a graph that I've taken from a paper by Chagas and Quade. This was published in an IFPRI article. I'm going to talk about IFPRI in just a second here, where they showed the effect of no additive in the blue line. If we look here, if we're trying to get a 10 micron particle size, they're going to take about 70 kilowatts per kilowatt hours per ton to grind up calcined alumina. But if you add a 0.1% alcohol, you can get it down to about 30 kilowatt hours per ton. That's a 2 times decrease in energy, really quite an interesting impact. In another paper, in a review that IFPRI also asked Quade to do, they found that this grinding aids are also useful in other techniques beyond ball milling. So it's useful in jet milling also, and it's actually useful in air classification. So this idea of using something to improve your energy efficiency, or actually read that the ability to grind faster, is something that we should all be aware of. I won't be talking about that today in the talk, but I just thought it was a very interesting piece of information for everybody to have and consider. If you want to be more efficient, consider using some of these grinding aids. And grinding aids can be as simple as alcohols or even waters that can be removed from the system after you use them. Just to mention IFPRI, I'm not only, Brent did not mention that I'm also the president of an organization called the International Fine Particles Research Institute. It's a consortium of companies that get together to look at the fundamental problems that industry has with particle processing, and grinding is one of these. And this is why we asked in this organization, asked Arno Quade in Germany to actually look at this for us, and he came up with some most interesting results. In essence, what he found was grinding aids, whether it is jet milling or ball milling, increase the powder flow. And if you have better powder flow, you have better grinding. So one of the interesting take-homes from this talk, I hope you take home, is that even though you might be really interested in grinding, you really need to be thinking about powder flow. You need to be thinking about drying. You need to be thinking about the amount of water, i.e. grinding aid, that you might actually have in there, purposely or not purposely. So let's consider classification. Classification, just like grinding, has been done by humans for tens of thousands of years. In essence, if the particles are big, we can actually grade them. So if you have big rocks and little rocks, you can actually pick out the big rocks one by one. You can grade those materials. About 4,000 years ago, I think it was in Egypt, they invented sieves. It was a classic way of doing classification or size separation for years and years and years. But also, I would say that grading and sieves are basically a physical sorting type of operation. But there is also a different type of classification or sorting, which I call medium-induced drag combined with attractive forces. And this is winnowing, basically throwing particles up in the air and having the fines blow away or the chaff blow away. Elutriation, passing air through a bed of particles and lifting out the fine particles. Air cyclones, which actually use a centrifugal force and medium drag to separate particles. And air classification, which I'm going to explain in just a second. These techniques, knowing these techniques, the easier that you can do it, like sieves or even grading, that's what you want to do. When you get down to air classification, we're using air classification because the particles are small and it's the only way that we know how to do a proper separation. So in separation, what we're looking at is we're looking at how well did we make the cut. Let's say that we want to cut at 10 microns, and that's what we're looking at. So we're going to want to know how many of the small particles didn't get separated and how many of the big particles went through our system to end up in our product. And basically what we do, we analyze this by looking at the steepness of a curve. This is a volume percent versus particle diameter. This is a real standard way of looking at particle distributions. And what people do is they look at the D90 over the D10. And if that is 1, basically what we're talking about is a very steep separation, which would be a perfect separation. But if it's a D90 over D10 that's less than 1, our classification isn't as good. We are always striving for a 1. We hardly ever get there. That's one of the things that we all have to know as we're grinding and then separating. We are always going to have some fines where we don't want them or some coarse where we don't want them. We're always looking for the perfect classification, but we hardly ever reach it. So let's talk about the actual mills that can be used, particularly in jet mills. Jet mills are, relatively new invention. They're just over 100 years old now. The first jet mill was made in 1917. It was an opposed jet mill. Basically, what people were doing were taking particles and training them in high pressure air jets and shooting the particles at each other. So they had two jets, opposed jets, and shooting them at each other, and they would separate, or they would grind this way. Now, in this type of grinding, they didn't do any classification. You'd have to separate your coarses and your fines later on. In 1934, there was another process that was invented. That was the fluid bed process. That also has a separate classifier. So you do the grinding and then you do the separation classification afterwards. In 1934, there was also a pancake mill. In 1940, there was an oval jet, and those actually have an inherent classifier. In other words, they're a simpler system. You don't need a grinder and a classifier, but they have a tendency to give a broader distribution of the final particles in a jet mill process. Give you an example. This is what an oval jet looks like, and this is very similar to what a pancake mill looks like. What you're looking at here, as you take a look at this, is you have an airstream that's going through this oval chamber, and going very, very fast. What it does is it pushes the large particles to the outside of the airflow. There's an inner release of air that is taken out of the system. The fines are entrained in that air, and that's how you get your separation of your fines, your ground material from your coarse. The coarse keeps recycling. The challenge with this system is that you basically set up your parameters with the airflow, and you have to accept what comes out of the end of the system. You can't modify your classification. So you change your parameters, you get a different size, but you're not controlling the particle size as well as you could. In the case of a fluid bed jet mill, these are the types of mills that Avika manufactures and uses. What we're doing here is at the bottom of the mill, there's jets that are in there that are using high pressure air that are actually causing the particles to collide with each other and grind up. You're putting the feed up in the top, and now at this stage you have a mixture of ground particles and particles that might be the right size. At the top of the chamber where the air is being released, all this air that's coming in from the jets is being released, there's actually a classifier. And you can see in the diagram here, there's a wheel that spins very, very rapidly. The more rapidly you spin, the finer the particle that's allowed out of the system. Larger particles are forced back into the grinding zone for grinding. So you can actually do grinding and then have a separate classification step that you can release out finer or coarser particles by controlling the speed of the system. An actual setup for a jet mill, and this could be a pancake mill or an oval jet mill, is basically you have your fluid bed system here with or without your air class, with the fluid bed with the air classifier. You're collecting your product in a product collection, a cyclone, a baghouse, whatever it is, and then you just have an air manifold exhaust on this system. What's nice about a system like this is that it's a negative pressure system, so you can actually run a fairly clean operation. You don't have particles flying all over the place. The only time that you have loss of particles is when you're opening up your system, but it's a relatively neat process to actually do. Now, the types of materials that are both ground and classified are shown here. And, it can range anywhere from ceramics to active ingredients, to cosmetics, to carbon blacks, to minerals, food. And what you can see here is all of us know that, yes, sure, we can do all of these products with a jet mill and an air classifier, but we can't do them all at the same time. We can't do them all in the same type of facility. So one of the things that we haven't talked about in the past is what sort of site operating requirements are had for processing these different types of materials. So for example, if you're handling an API, personal protection equipment is going to be absolutely critical, because even if you have a good control of the material, there is always the chance that some of those materials could get out and you could be exposed to high concentrations of materials that you really don't want to be exposed to. One of the other issues, because we are taking bigger particles and grinding them down to smaller particles, as we grind the smaller particles, if the material has a combustibility, it's only going to get worse as we grind it. So one of the issues that really has to be addressed with whatever you're handling, do you need to have dust explosivity or explosion suppression on your systems? Cross-contamination, one of the things that's happening nowadays is there's a lot of interest in batteries, and one of the materials in batteries are typically heavy metal oxides. And so even if you have a negative system that everything is enclosed, one of the challenges of handling heavy metal oxides is that you don't want to contaminate the room that you're in. You don't want to take that heavy metal out into the rest of your plant. So, how do you actually do that isolation? And finally, there's all the quality issues. So if you go from, chemicals that you can process with, some quality control, but if you start doing drugs or food or cosmetics, the issue becomes even more critical, because they have some very specific requirements: materials of construction, control of the materials. How do you maintain the non-contamination? The picture that I'm showing here is one of the issues that we're dealing with right now. This is a new filter receiver that's part of a new jet milling system. That what we're doing is we're building it out of stainless steel as opposed to carbon steel that many of the systems that we have. So you can see it's stainless steel. You can also see at the top here these two red canisters. These are explosion suppression devices, because in this particular case we're processing a polymer, so we need to explosion suppress the system. And finally, because in this particular case we're building this for a cosmetic application, we're changing the quality requirements that we have. So you can handle all these materials, but you have to have absolutely the right facility to be able to handle them. And this is just an example of some of the things that we think about, or anybody thinks about, when they're handling this. Just want to talk a little bit about classification, because we're going to talk about it in just a bit. This is a cross section of a classifier. Basically, what we have here is a wheel that is spinning. We have feed that's coming in this side port here. So this would be the coarse material or the feed material. It's basically going in here. It's moving very rapidly around this ring, so that large particles are being forced to the outside. The airflow that's going through the system allows you to take the particles that are small enough to get through the speed that you're operating this rotor, and you can get your fines that come out here. The coarse actually goes back. In this case, this is a closed loop system. We take it to a opposed jet mill. We're doing grinding, and then the recycle goes back in here until it actually gets down to the right size. But this idea of being able to separately separate, as opposed to having the classifier and the grinder all together, is one that we're going to show you some reasons why we want to do this in the next couple minutes. So, we talked about, what are the processes for grinding. We talked about, specifically jet mills and air classifiers. We talked about the energy usages and perhaps being able to use some grinding aids to do this, but let's actually talk about some examples of what we're doing. So the first one, let's talk about grinding and classifying a ceramic mineral. And we want to do this at different rotor speeds so we can get different particle size. And after we've done this grinding and classification, we want to further classify it to get rid of the fines. So over here in this slide, what I'm showing you is our starting material that starts out at 177 micron D50. Just a standard nice Gaussian distribution. This is a ceramic material. And just to kind of repeat what we're doing here, we're going to be jet milling in this jet mill chamber in here. And then we're going to be changing the rotor speed here so we can get out different size cuts. So let's just take a look at what happens.
So
here's where we do a low rotor speed, and we're going to get out a coarse particle. So we went from 177 microns to 34 microns, and you can see the distribution here. You can also see that there's a substantial fines tail on here. So, this stuff was grinding fairly rapidly. We couldn't get out of the system before we had fines. When we went to a higher rotor speed, which means now it's going to keep the particles in the system until they get smaller, we can get down to a 14 micron. Now these distributions are tight. These are okay, but they could be better. And just to give you an idea, this is what the starting material looks like. It was 86 to 285 microns. It's a chunky ceramic material. After we ground it, the coarse grind, gave us a 7 to 65 micron. That averaged 34 micron particle size distribution. And the fines, you can see, are substantially finer. But what you can see in both the coarse grind and the fine grind is all the fines that we saw on the distribution. You can see fines here and fines kind of scattered out here. So in this particular case, the need was for a tighter distribution. So we could control the distribution, but could we get it tighter? And the answer was, of course, yes. This is what it looks like after we sent it through our classifier, our standalone classifier, and we classified out that big tail of fines that you remember that we saw there to get a 73 micron final cut. We also did it with the fines, the high-speed rotor, smaller size, that started out as 14 microns. We classified out the fine tail, and we got a 19 micron. But let's just see, I like particle size distributions, and we do a lot of particle size distributions, but at the end of the day, I always like to see what does the system look like. So you can see here this coarse product that was 34 microns that went to 73 microns. The fines are gone. I mean, it's a incredibly clean product. And the same for the smaller product that went from 14 to 19 microns. You can see many of the fines, most of the fines, in fact, are gone from this product. Exactly what we were looking for. So the challenge is, wouldn't we like to have gotten this on the first step? And perhaps we could have optimized this with our grinding parameters, but in this particular case, we were able to show that we could grind it and then classify it to get a very nice tight distribution. But what if we don't want to grind it? We just want to classify it. And this is a case here where we're gonna take glass beads. This is the classic glass Ballatini that everybody talks about, that we're gonna classify this. So we have a distribution. The starting glass has a D50 of 33 microns and a D10 of 19 microns and a D90 of 48 microns. There's a tail here. We want to get rid of this tail. That's what we're really trying to do. And our customer really wanted to have a tight distribution. They wanted to, get this distribution from about 25 microns to 48 microns. You can see that's the green list that you can see on the green particle size distribution you can see here. But we looked at this and we said, let's just expand this just a little bit. So going from a D10 of 25 microns to 24 microns and a D90 of 48 to 50, basically we're increasing the span 3 microns. And we're looking for what effect is it going to have on the product and the yield. So let's just take a look at what the next slide shows here. And you can see here's our starting beads, nice round glass Ballatini. Here's our two cuts, the narrow cut and the broad cut. They look about the same. The broad cut has a few more fines in it, but not too bad. But look at the yield. That narrow cut is 43%. The broad cut is 73%. To me, this was astounding. For a 3 micron cut over or expansion of the cut, we almost doubled the yield of the product. And I think it's a real important aspect to consider. Sometimes many of us, not all of us, many of us get stuck on, this is what I need, I don't want to have any change from it. But sometimes you need to look at, changing your outside parameters just a little bit, and the effect can be phenomenal. In this case, almost doubling your yield. Well, let's look at one other classification where the raw material, in this case, we don't have to grind it, just like we didn't have to grind the glass Ballatini. This is a silica, a pre-ground up silica. It comes in at about 11 microns, pretty tight distribution, but the customer really wanted to get rid of just the edge of the fines. And so we did a first pass where we're just taking off the fines edge of the material here, classifying it, and we went from 10.97 microns average particle size to 11.43. And then we sent it back through the system and took off another half a micron. So, you know, the question is why didn't we do this in one step, and what difference is it really going to make? It made it perhaps a little tighter, but let's take a look at the SEMs here. So here's the starting material. You can see the big particles, and you can see a lot of fines that are in there. Here's after the first classification. You can still see the big particles, and quite frankly, when I look at that, it looks like there's more fines in the after classifying it than it did to start with. But look what happened after the second classification. The particle size went up a little bit, just like we talked about on the previous slide, but those very fine fines went away. This is one of these really interesting things about optimizing your process. In this particular case, my guess is what we did is we loosened up the fines on the first classification and took them away on the second. Now, why that didn't work in one step, I'm not sure. That's a really good fundamental question that should be looked at. But this is one of the things that we see in industrial processing again and again and again, this need to kind of fiddle with the process parameters, even though you think you've got it right, to really get the final product that you want, because ultimately the real need was to get rid of all those fines. And it took 2 classification steps to do it. Well, let's look at a grinding where we're comparing jet milling to ball milling. Now, both these processes work. They got to the right size. You can see the distributions shown at the bottom, the D10s to the D90s. But you can definitely see the ball milling seems to have more fines. Now, if I had to take a choice on which process to use and money was an object, I would pick ball milling, because ball milling is always going to be a cheaper process than jet milling. But you know what was interesting on this was the creation of more fines. You can see it in the size distributions, and if you look at the pictures, here's the zircon sand that we started with. Here's the SEM picture of the ball milled zirconia, and here's the jet milled zirconia. You can actually see the more fines in this. And if fines were an issue for you, whether it's because it's a dusting issue or whether it's a powder flow issue, you would probably be looking at jet milling instead of ball milling, even though the process is more expensive. Now, you know, I've talked about jet milling. I've talked about air classification from just a size control. And you know, really, when I think about jet milling and air classification, I'm really thinking size. But let's look at a different problem that we had. We had a customer that came to us and asked us to ball mill and jet mill cellulose fiber. And what I have here is just raw material cellulose fiber. You can see, you know, these are wood pulp cellulose fibers. They look flat, but in reality, when you really look at them, if they were in the wood product, they're fairly round. They have a hole down the middle. These are like straws. Basically, cellulose fibers are like straws. And these circles that you see on the side here is the way the water gets into the straw and leaves the straw, because the cellulose fibers are what's taking the water up the tree, out the leaf, you know, wherever it's going. This is the water transport system in any plant in the world. Now, what we did is we took this untreated cellulose fiber that you see here on the left, and we ball milled it, and basically we folded it over and broke it up. And so basically it's just like taking paper and folding it up. But when we jet milled the fiber, we got the structure that you see on the inside. And I'm not talking about particle size here now. I'm talking about form. And I find this incredibly interesting. We think about jet milling as a way for size reduction, but is there something else that we can do with this? So let's just take a break here from these examples and look at jet milling to what I call new forms. You know, basically, as I said, size reduction is the standard method that we're doing, that we're using jet milling for. But I think there's a reason to believe that jet milling can also be used for morphology development. And basically, that morphology development is really looking at, can we change the functional characteristics of the material after we've processed it? So in the case of food applications, you can actually change the water absorption by changing the morphology. In the case of ion uptake for battery materials, by changing the morphology, you can change that ability to uptake lithium ions or other materials. And for powder flow, for 3D printing, if you can change that morphology, you can actually change the ability for this material to act as a better 3D printing material. So let's actually take a look at this, and let's actually look at a little bit more closely what's going on with this cellulose fiber. So once again, here's an SEM picture of cellulose fiber after it's been jet milled, and you can see this, you know, almost explosion of fibers coming out all over the place. You can see some aspects of the fiber, of the raw material fiber, but you can see all these microfibrils in here. If we look at the structure of cellulose, you can see on the right side here, you can see the hole, the lumen down the middle. So basically we have a long straw, but the straw is not a one-walled structure. Cellulose is 3 to 4 walls, and basically it's microfibrils of cellulose that are wrapped around the center in different orientations. So one might be straight across, one might be at a slight angle one way, one might be at a slight angle another way. And basically what happens is these microfibrils are 1 micron or less in diameter, whereas the cellulose fiber might be 10 or 50 microns in diameter. And what happens is when we jet mill it, we break this up and we start breaking out these microfibrils that we see here. Now, this is actually significant in processing. In food applications, what happens is cellulose itself has the ability to hold about 2 to 3 times the amount of water. If you microfibrillate this cellulose, it has the ability to hold 20 to 30 times the amount of water. So it's a very interesting way to get away to controlling the water in a food application. Alternatively, in paper making, if you want to make stronger paper, you actually also microfibrillate, and they can do this in a liquid process, which is the way that paper is obviously made. And you can get this. I strongly suspect that jet milling microfibrillates even more than standard paper making processes. So here's an example of jet milling actually making a brand new structure that's never been seen before. Well, are there other examples that these things happen? So here's an example where we took a polymer that has a fibril structure, you can see there, and we jet milled it. Now it broke apart the major big fibrils in there. You can see that on the raw material versus the jet milled. But interestingly enough, we've started to form microfibrils again. Now we didn't optimize this process to maximize the microfibril. My suspicion is we could make this really interesting and really fuzzy. And then you're starting to ask the question, so what is it good for? That functional characteristic. Is it a water holding? Is it a stronger material? Is it a blah, 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 blah? Once again, jet milling is not just a size reduction, but it's a new form production. In the case of batteries, we are seeing all types of different carbons being used, for the last 10 years. There's carbon black. These are all starting materials. These are from the literature. carbon black, graphene, which is a platy-like structure, coke, which is carbon coke, which is formed from biomatter that has, fractions of the carbon removed, and you're left with really either solid structures as shown here, or you can get some very open pored structures here. And finally, carbon nanotubes. These are all forms of carbon, and they're all being actively looked at in batteries for better conductivity, for better spacing, for better ion control within the batteries. So let me give you a couple examples of what we've seen. This is a case of coke that we ground. It was basically chunky material, and guess what? At the end, we still have chunky material. We don't see that fine structure in here. I think it has to do with the nature of the starting material. This still had a higher surface area, and it was, to be honest, we don't really know what they were going to use it for, but higher surface area, better packing, perhaps better conductivity. The one that I find very interesting is when we took graphite and jet melded, and if you look here, you can see the platy structure all over the place, just exactly what you'd expect from graphite. But if you look closely, some of these smaller structures almost look like the start of graphene, or the single layer carbon formation here. I'm not sure that we are getting to graphene, but it's an interesting way, instead of going through the chemical exfoliation methods that they use to produce graphene, we can actually use a physical method to maybe get, graphene wannabe. It might have some of the similar characteristics. So very interesting. Jet milling is not considered a exfoliation technique, but here we're actually seeing exfoliation and a new product form coming. Now, when I saw this picture of something that we had jet milled, I thought, how the heck did we make beads? I see jet milling be a random breakage process. I see jet milling be a not something that's going to round off materials, and yet I'm getting beads here. Well, the answer to this is a final product here. The answer here is you could obviously see agglomerates in here. So in this case, were we really grinding? We were size reduction, but we were really de-agglomerating. And so in this case, de-agglomeration became important, and the structure that we were getting for the primary particles wasn't a breakage of those particles, but actually the release of the final particles. So we were making spherical particles in a technique I wouldn't have thought could make spherical particles, but did in fact, because we were just releasing those primary particles from the structure. Similarly, from a de-agglomeration standpoint, here we have a big raw material particle that looks like a ball of fur. It turns out it's a ball of needles that when we jet milled it, we didn't break the needles, but we broke the needles apart. So one would think that this is a way of taking some of these products that already have a functional property in there, the crystalline needles, and get it to be dispersible and usable in a different form. Once again, we didn't make needles, but we released the needles that were in that agglomerated structure. And finally, my last example, I think I'm actually even on time this, for the first time in any HORIBA talk I've ever given. We also looked at a lot of solution deposited materials. Now, these are typically used in 3D printing, and so you get kind of a globby structure here, the starting material. And when you jet mill it, you're starting to break up the agglomerates once again to get structures that look like this for one type of polymer, or structures that look like this for another type of polymer. These grindings are done to improve the functional characteristics during 3D printing and to improve the flowability of it. So what we've talked about today, and I hope this has been interesting to you, is we've talked about jet milling and air classification, the methods that we use, what we can get for different sizes, and how tight distributions that we can get in that 1 to 75 microns. We've shown that optimization might have to take a couple steps. You might have to classify it or grind it a couple times in order to get it. Most interesting to me in this talk, we've talked about, jet milling not as just a size reduction, but a way to make new material forms. And I think we should be looking at this more often. This obviously requires the use of both particle size distribution and SCM analysis. It's always material dependent, and I think at least with these new forms, if the structure is already in the new form, so if we can get that new form, if we can understand what's in the new form, maybe we can get even more interesting structures out. And I like to point out that a lot of this processing, whether it's jet milling, classification, spray drying, or any of these things, it's all about, do you know the tricks, and can you use those tricks to get the best possible optimum final product? And I want to thank everybody for listening, and I think we have time for any questions, and I'd welcome any questions that you have. Thank you.
We do have some questions rolling in here. The first one is, can you comment on elbow jet classifiers versus rototype classifiers?
Elbow jet versus rototype. So, are they talking about a pancake mill versus an oval jet type of? We typically use either a pose jet, or we use pancake, pose jet or fluid beds. We haven't used the pancake mills, although we have had a little one in the past, and just find that the size distributions are broader. So I'm not sure if I'm really answering the question or not. I'm not quite sure I understand, but that's as best I can do. Sorry.
Okay, no problem. Next question: where do pin mills fit between air jet mills and hammer mills in terms of PSD produced?
So pin mills are going to give you a smaller particle size than a hammer mill, and if you actually add a classifier onto the pin mill or an air classifying mill, you can approach a hammer mill, or excuse me, a jet mill. Usually that jet mills can usually get a little bit finer than an air classifying mill, and pin mills aren't quite as good as an air classifying mill, but they're a little bit better than hammer mills. So hammer mills, we like to think that we can get down to 75 to 100 microns, and pin mills, I've seen people get down to 30 microns with them.
Okay, thank you. How would the pressure of the air affect the work of a jet mill?
That's a great question. I didn't talk about that, and I should have. It turns out that the higher the pressure that you can put into your jet mill, whether it's a fluid bed or a pancake mill or any of these, the finer the grind that you're going to get. And ultimately, what you end up with is, with air, you get limited by the compressors and how much air that they can deliver at higher than 120 psi. So what people have done to get very finer grinding with a jet mill is that instead of using air, they'll use steam, because steam you can get up to 300, 400, 500 psi very easily, and so you can get a much finer grind like that. So that's whoever asked that question, that was a very good question. You typically get limited by your compressor, so you go to steam and you can get a finer grind.
All right, thanks, Willie. That was Ahmed that asked that question. Looks like we do have a pretty active audience here. We've got quite a few questions coming in. How about acoustic mixing? They're aware of mixing being used for pharmaceutical milling, but curious if it has other uses too.
So I'm familiar with acoustic mixing. So the Residine system, is an acoustic mixing system. There's also a mixing system called a FlakTech, which is a centrifugal mixing. Those processes can be used for milling. We've used them. Haven't used the Residine acoustic mixing system, but have used the FlakTech, the centrifugal mixing. Incredible processes. They're great systems. Incredibly difficult to scale up. So if you need to make grams of material, or maybe even a pound of material, an acoustic system or a centrifugal system for a grinding process, it's a great thing to have in your lab. Every lab should have one or the other. But when you scale it up, it's a challenge. So if you're a pharma company or maybe even a cosmetics company, you can conceive of having multiple pieces of equipment to do that type of grinding. But if you're trying to do anything beyond pounds of material, it's going to be very difficult to scale that process up.
Okay, thanks for that. We actually had a follow-up from Ahmed. Will the erosion of the air nozzles affect the pattern of the milling?
Absolutely. What will happen is as those nozzles, and they absolutely will erode. Ahmad is absolutely right on this, and so people actually use ceramic nozzles, tungsten carbide nozzles, to minimize that wear pattern, because as it wears, the jet is going to open up, and it's not so much the pattern, but obviously as the orifice opens up, the pressure drops, so you start losing your efficiency.
Okay, thank you for that. Kathy asks, will moisture impact hammer milling also?
Kathy, I'm not sure who you are, but that is the question to always ask. If we are working in particle processing, the question that should be uppermost in our mind is always moisture. I would say that the answer to your question is moisture will affect everything. It will affect hammer milling. It might be a slight effect, or it might be a huge effect. I'll give you an example. We were ball milling. This is not hammer milling, but we were ball milling ceramic material, and we found out that the changes in relative humidity in Minnesota in the summer to the winter changed the ceramic ball milling efficiency. So I can absolutely believe that your hammer mill can be also affected by this. We address this by adding water as a grinding aid and making sure the water content was always equal. So you can obviously do this by controlling your room environment or your air that's going into the system, or you can add a little grinding aid and control it that way. By the way, I should say, because Kathy, that's a great question. If any of you want copies of those two papers that I listed, unless you're an IFPRI member, you can't get them. But if you send me an email or write on one of your requests that you'd like to get those papers, I will send you copies of those papers, because they're worthwhile to read for sure.
Excellent. Thanks, Willie. I'll keep an eye out for requests for those as well. Do you have any experience of uniform mixing of 2 or 3 precursor materials using jet milling?
We have done something like that occasionally. So if you want to use jet milling to do a grind and a blend at the same time, the challenge always will be, if you're using jet milling, that's a great question. The answer is we do have experience with it. We have made it work, but if you get distribution changes, you're going to get output changes. So long as your distribution remains the same, you'll get that same distribution. You might send in a 40-60, but you might not get a 40-60 out, just depending on that size distribution that's going to come out. It's always a challenge to try to get two things to grind at the same time in consistent fashion. I think it's always worthwhile to consider it, but there's always that challenge that you'll have an upset condition and get a really different output. So I think there's reason to want to do it and reason to be very cautious.
Okay, we've got time for just a few more questions. Do you have any information you can relay about jet milling or milling resistant food fibers? He gave rice bran, oat bran, or sunflower husks as an example.
So we've actually ground rice bran, and the person who's asking that question knows that it's an incredibly abrasive material because of the silica content. They grind. They do wear your systems quite interestingly enough. Unless you really had to go to that fiber structure that I was showing for a rice bran, I would probably use a ball mill, and ball mills grind up that stuff very, very nicely. You can get down to a very nice fine size on that. The other boy, I'm trying to think. We've ground corn hulls and we've ground oat hulls also. We didn't do them in jet mills. We did them in hammer mills, to be honest. We didn't need to go to that jet milling. Always a challenge to handle those materials because of the powder flow characteristics and the oddness of grinding. This would be one to talk about if they want to contact me. I'd love to talk about it. But it does grind. All these materials grind, but they always have their challenges.
Okay, thank you for that, Willie. I think we have time for just one more question. If we didn't get to your questions, we'll follow up with you afterwards, or you can always write Willie or labinfo@horiba.com if it's a HORIBA question. Last question, can nanotube materials be deagglomerated by jet milling technique?
The answer is yes, up to a certain extent. I mean, are they going to be completely deagglomerated? I mean, you have a lot of contact points. You have very small particles. You have a very lightweight material. There's not a lot of forces to help you get it done. We've deagglomerated them occasionally. Don't have tremendous experience on it, but the answer is yes. Worthwhile to give it a try again if you're interested. But is it going to be agglomerated enough for you? I mean, typically when people are talking about deagglomerating nanotubes, it's always that issue. Is it going to break the nanotube? Is it going to get you enough deagglomeration? Typically, we've done this in liquid as opposed to jet mills, but it does work to some extent for sure.
Excellent. Well, thank you so much for your answers there, Willie, and the fantastic talk. We really do have quite a few questions rolling in. So if you want to either follow up with us, we're at labinfo@horiba.com, or if there are questions for Willie, you can reach them. I believe it's avika@avika.com. Is that correct, Willie?
Absolutely. And we will follow up with all the questions that you have. So please pass on any more that you have. And once again, I'd really like to thank all of you for listening to my talk and for all the good questions. Really appreciate it.
All right, thank you so much. And on behalf of Willie and Avika and our particle group here at HORIBA, thank you for attending, and we will see you next time.
Take care.